Swayam Prabha. Digital India. Educated India.
Good afternoon. Last lecture we started with various aspects of pile foundation. First I told you that what exactly do you mean by pile foundations and why it is required. That when the above soil strata is not good or poor in nature, that it is unable to take the load which is coming from the superstructure, then we need to extend the foundation to the larger stratum. And those type of foundations, they are called deep foundations, and pile foundation is one of that type. And then we discussed that what are the various types of pile foundation depending on the load transferring mechanism. Piles can be classified as point bearing pile, skin friction, then compaction pile, tension pile, etc. Then depending on the material of construction of pile, these can be classified as timber piles, then we had steel piles, and then we started with concrete piles. In concrete piles there were two types of piles, one was bored cast in situ and another was driven precast concrete pile. So we saw that what are the main features of these piles in the last class. Today let us try to see that what are the various advantages and disadvantages of these two types of concrete piles, how one can be superior to another, or what exactly is the disadvantage or advantage of one particular type to the another one. First starting with advantages of driven cast in situ piles. Once again I would like to recapitulate that what are these words mean by driven is that you are driving it by any mechanical mean, by hammering or by vibration. Cast in situ, it is getting casted at the site itself. They can be driven to a predetermined set. Pile lengths are easily adjustable since they are being casted at site only. So let us say at the 11th hour you change the length of the pile, then that can be taken care of. An enlarged base can be formed which will help in generating much higher end bearing capacity in a granular bearing stratum. Let us say that you are driving a pile in a granular bearing stratum. Then towards the end of the pile, that is where its tip will be resting, there you can provide an enlarged base which will result into larger bearing capacity. This aspect also we discussed in the last class. This case reinforce is not needed to take care of handling or driving stresses. Piles can be driven with a closed end so as to exclude the effect of groundwater. Let us say that while driving the pile you come across somewhere groundwater table. So if the pile is driven with closed end, there you will not be having any effect of this presence of groundwater table. Some of the disadvantages of driven cast in situ piles, that heave of adjoining ground surface which could not affect the services of structures or nearby. That is, let us say a very sophisticated structure is there nearby, in nearby location, that doesn't you have to protect that from any kind of vibration. So in that case, while driving the pile there will be lot of vibration which will take place and the heave also can occur. So that is one of the disadvantage of driven cast in situ piles. Lifting of previously driven piles where the penetration of the pile toes into the bearing stratum has not been sufficient. So that is again one of the disadvantage. Possible damage to uncased piles by necking or wasting due to lateral forces when the concrete is green. Let us say the concreting is going on and the concrete is green. In that particular case, the and in case of uncased pile, that is when after concreting you are not taking out the casing out. So, you are taking out the casing and that type of pile is uncased pile. So, possible damage can be there. Then concrete cannot be inspected after completion. Concrete may be weakened if artesian flow pipes up the shaft of pile when the tube is withdrawn. Again, this is when the concrete is weakened, obviously the pile bearing capacity will decrease. So, that is not desirable. So, it becomes one of the disadvantage of driven cast in situ piles. It cannot be driven where headroom is limited. Then limitation in length because of lifting force required to withdraw the casing. So, let us say in case of uncased pile you have to take out the casing. So, in case of higher length of the pile, the lifting up of the casing becomes more and more difficult in case of driven cast in situ pile. The maximum pile length which you can go for in case of driven cast in situ pile is of the order of 25 to 30 meter, and allowable load which any driven cast in situ pile can take depending on the soil condition can be of the order of 1500 kilonewton. Now, some of the advantages of bored cast in situ piles. What do we mean by bored? Word here that you have to first create a void by boring or some excavation measure, and then you have to fill that with concrete which will form as bored cast in situ pile. Cast in situ, it is getting casted at the site only. Very little displacement or no risk of ground heave. As you know that this falls under the category of non-displacement piles. So, in this case, and there is no mechanical hammering which is taking place while driving this kind of pile. So, very little displacement is there and there is no risk of ground heave at all. Length can be readily varied. Soil can be inspected and checked with soil investigation data. See, when you will be creating the void or excavation, so whatever is the soil that you are taking it out, you know at which particular depth you are taking that soil out. By examining that particular soil and by comparing with the soil exploration data, it gives you the check whether your soil exploration data is proper or not. It just confirms that information. Piles can be installed in very great lengths and very large diameter. This is one of the main advantage of bored cast in situ piles. End enlargements of up to 2 to 3 shaft diameters are possible in clay or soft rocks. See, in the earlier case it was for driven cast in situ piles, it was the enlarged base was able to form in granular deposit. However, in case of bored cast in situ pile, this end enlargements can be possible in clays or soft rocks. It can be installed without much noise and vibration and with limited headroom. Now, some of the disadvantages of bored cast in situ piles, that boring methods may loosen sandy or gravelly soil. See, if the soil is of clayey in nature, then this bored cast in situ piles are quite advantageous. But in case of sandy or gravelly soil, in the process of boring or excavation or creating the void, there can be loosening of the soil strata, which is not at all desirable as far as construction is concerned. Concreting underwater will pose problem because it is cast in situ, you are creating a void and then you are filling that with concrete. So, in case if the water is present somewhere along the length of the pipe, that can pose the problem. Then concrete cannot be subsequently inspected. Once you have, see, the thing is, once you have created the hole of, let us say 30 meter depth, then you have to go on pouring the concrete and then go on compacting it, but we really cannot inspect that to what extent it has got compacted, whether we have achieved the desired degree of compaction of concrete or not. So, that becomes one of the disadvantage of this kind of piles. Now, these are susceptible to wasting or necking in squeezing ground. Enlarged bases cannot be formed in case of granular soil. In case of clayey soils, yes, you can do that, but in case of granular soil, it is not possible. Then every time we are talking of enlarged base or say providing little more cross section as compared to the pile shaft. So, these kind of piles, they are usually called as under-ream piles. Let us see that what exactly are the few features of these kind of pile. An under-ream pile is a special type of board piles which is provided with a bulb or pedestal at the end. So, enlarged base, it forms a kind of bulb that we call as under-ream piles. It is constructed by making a hole in the ground by means of hand operated auger. So, what are the steps, how it is being carried out, how it is being constructed, that we will be discussing one by one in the subsequent slides. An under-reamer is then lowered in the cleaned hole. So, first a hole is created, a bore hole is created, then you can insert an auger into that, and by hand operation you can increase the diameter at the end, and then an under-reamer is lowered in the bore hole which has been cleaned. The under-reamer is pressed down and rotated. Then under pressure the blades open up, the blades of under-reamer, they opens up, and due to rotary action the soil is cut and falls in the bucket. So, once the bore hole is created, you insert the under-reamer and then with pressure you try to rotate it. So, as soon as it there is some pressure on the under-reamer, its blades get open, and with the rotatory action in the clay part or in the soil part there below at the end of the pile, what happens is the soil is getting cut and then it falls into the bucket associated with it. When the bucket is full, under-reamer is pulled out and cleaned. So, the soil is being cut, it gets accumulated there in the bucket associated with under-reamer, it is then pulled out and then it is cleaned. And then this process is being repeated again. So, the under-reamer is lowered again and the process is repeated. After the enlarged end is formed, the reinforcement cage is lowered and the concreting is done in this case. So, you see here with the help of figure, if I explain you. So, first this hole is prepared, that is called bore hole, that is boring guide. With the help of this you inserted the auger. See, it is of this kind of shape. Now, what happens is with the auger you just put the rotary action and then you take out the soil. So, this is the process of preparing this bore hole. Once this bore hole is prepared, you insert the under-reamer. It is of this shape and then you apply the pressure from this point. What happens is its blade get open up, and and if you rotate it from this point, that is top, the soil at this particular level will get cut and it will get deposited in a bucket which is with this particular assembly. Then you simply take this out, empty the bucket, put lower down the under-reamer again. With the pressure again the blades will get open, the soil will get cut, and then you can take out the soil. You can repeat this process again, and then you can simply lower down the reinforcement cage in this particular manner, and then the concreting can be done. So, these are the various stages in the construction of single under-reamed pile. Now, these under-ream piles, usual size of piles is of the order of 150 to 200 millimeter shaft diameter. Usual length of piles, they are 3 to 4 meters length. Diameter of under-ream portion 2 to 3 times the shaft diameter. So, if a pile is having a diameter of, let us say, 500 mm, then you can go for the size of the bulb for 2 to 3 times at 500 mm. But usually in case of under ream pile, the diameter of the pile shaft is of the order of 150 to 200. So, let us say if it is 150, then the diameter of under ream portion can be 300 mm to 450 mm. These are considered useful in case of expansive soils where the use of shallow spread footing is ruled out due to excessive shrinkage and swelling behaviors of such soil. You know that expansive soil with the presence of water or with the increase in temperature, they frequently either shrink or get swelled. So, in that case the shallow footing does not serve the purpose. So, therefore, the deep foundations, they are usually recommended for such type of soils, and in those type of soils this under ream piles, they are proven to be very useful. When the number of bulbs is increased from 1 to 2, the carrying capacity of pile increases by about 50%. This is just a rough idea. It is not a hard and fast rule that it will get increased by 50%. It will all depend upon what is the type of the soil which is surrounding the pile, and then what is the bulb diameter or what exactly is the spacing. So, all these things you have to design in case of under ream piles. Let us see some of the experiences that I had at one particular site where this pile driving and the construction of pile was going on. As I told you that in case of driven precast piles, what happens is your piles, they are casted at some particular workshop, and then they are being transported to the site, and with the help of driving rigs, they are being installed in the ground. So, while driving the pile, lot of hammering and vibrations they occur. So, you can see here it is such a huge driving rig. You see when it just hammers one particular blow to the pile, how much noise that it will be creating, and if there is some sensitive structure nearby, then it can cause problem to that. But in case of barren lands, you can see here that nearby there are no structures, only some trees and some barren land it is there. So, that is why at this particular site they could go for these driven piles. And then when we were dealing with the person who was taking care of these construction of piles, he usually told us that usually this in case of driven piles, they go for 550 mm diameter in India. So, this becomes a limitation of driving the in case of driven piles. However, in case of board cast in situ piles, you can have the diameter of the pile as large as up to the extent of 1 or 1.5 meters. So, you see this is the assembly, it is kind of driving rig, and here there is one hammer, it is just centered at that particular point where you have to drive the pile, and just with hammering the pile is getting driven. You see with the help of cables, you can see here, and then some of the cables they are here, it is held vertical in position. Then that was in the case of driven piles. In case of bored piles, first you have to prepare the bore hole, and then let us say the soil you have to go for say 25 to 30 meter pile. So, for that much depth of the pile, when you prepare the bore hole, you have to make sure that the wall of the bore hole they should not collapse. So, for that you have to provide either some temporary or a permanent measure to stabilize the walls of bore hole. So, what happens, either you insert a casing and then do the concreting and remain the left the casing as it is in the position, or another method can be that with casing you pour the concrete, when the concreting is over you take out the casing. Out of these two, usually there is the third one which is being used in the construction procedure, is that you know the bentonite soil. You know, a pond of bentonite slurry is being created, and with the help of one pipe, this bentonite slurry is being filled into the borehole which is prepared for the concreting. So what happens is, this bentonite slurry, it gets in contact with the wall of the borehole, and then it for the time being it strengthens the wall of the borehole. So you can see here that it is filled with this bentonite slurry. You can see this is the circumference of that borehole. This much part is being seen here in this particular figure. Then what is done is, with the help of a pipe, this bentonite slurry is getting filled into this, and there is another pipe which takes out this particular slurry. That is, once the this slurry is being has come in contact with the soil which is lying at the wall of this borehole. Once it get stiffened, the wall of the borehole get stabilized. So what happens is, then you can take out the remaining slurry which is lying there in this, and then with the help of water you have to clean the hole, because if this bentonite slurry remains in the borehole, while concreting, concrete will be in contact with this bentonite, not with the soil which is really lying over there. That is not a desirable situation. So you see here a worker, he has put some weight is there. With this cable, he is trying to measure that at what particular depth the soil has been taken out. See, you have to go, let us say, for 30 meter. So there should be some measure to ascertain whether you have reached to that particular 30 meter length or not. So this is a kind of check that they provide at the site. Then lowering of reinforcement cage in borehole. See, if you are going for 30 meter long pile, then the length of the reinforcement cage will be of that order. And you can see it becomes like these are all steel bars, and there you can see here these circular ones, rounded ones, they are ties which tie these vertical main reinforcement of the pile. So while lowering it down, you see at a stretch you really cannot prepare a reinforcement cage of 30 meter, and in one go you really cannot lower it down. So what happens is that first they prepare a reinforcement cage of, let us say, 10 meter, they lower down it to some depth, then they hold it back, they weld the another reinforcement cage of 10 meter. Once it is getting welded, then they lower down this remaining part, and so on. So in one go it is not being lowered. So you can see that with the help of this rig, they just go on lowering this particular reinforcement cage. Then, as I told you that in one go you cannot lower this reinforcement. So you see, to kept this reinforcement cage in position, what is the kind of arrangement that usually at site they go for? It is like a bamboo, this thing, slab kind of a thing. They just place it in this borehole, and then you can see that they have made it rested with the help of this lateral reinforcement. You see, these are what are vertical reinforcement bars, they are main reinforcement. However, this one is lateral reinforcement, and these are lateral ties which are either wired or welded to the main reinforcement. So this is how they place or keep this reinforcement in position, that is, some of the portion is inside the borehole and some is outside the borehole. Why it is done, that will be clear in this one. You see here, this is this bamboo that you are seeing, with the help of which the reinforcement has been kept in position, and you can see here that this particular labor is welding here. You can see. So you see, this was up till this one, there was one reinforcement cage. Most of the portion has been lowered into the borehole. However, with the help of this rig, another reinforcement cage has been lowered to the extent that this particular worker is welding it. So, once it is getting welded at all the location, what happens is then you can proceed the lowering down of this particular reinforcement cage. So, now I hope that now you can appreciate why it is necessary to hold the reinforcement in position using this particular measure, so that the work which has to be done above the borehole can be conducted in this particular manner. Then you can see here that a particular reinforcement cage is lying. See, these are longitudinal reinforcement, these are the, you can see here, this is the particular ring which is the your lateral reinforcement, and these are your ties. You can see here, these are ties to bind this vertical bars in position. Then you can see there is a slab, sort of cylindrical kind of a thing with a hole in between. You can see here in this one. See here, this is a hole and this kind of thing is there. You see, this facilitates when you lower down this reinforcement cage in the borehole, it should not get in contact with the wall of the borehole. So, it gives you, it works as a spacer plus being of this shape. It is not fixed, so it can rotate. So, it facilitates the lowering of the reinforcement cage in the borehole. See, all these things you will not be getting in any of the books. It's just that the experience that we get from various sites, because not even IS code, any standard book, they do not give any specification that you should provide such kind of disc while going for this lateral ties and all. But then to ease in construction, to ease in workmanship, all these measures are taken care of while construction is going on. You can have a look here, this is a completed pile, it was of 1 meter diameter when we were there at the site. So, we recommended that 1 meter diameter pile should be there. So, this is how it looks with reinforcement and all, all the concreting has been done, and then from top also all the concreting has been done, and it is quite clean if you see. But if you see the subsequent slide, then you will really get the feel that how exactly these pile foundations look like above the ground. So, you see here, these are the group of piles. As I mentioned you that you never go for one particular piles, it is always that group of piles they are provided. So, you see, this much excavation has been taken place, and then you can see here that two views are there. These are all completed piles, and here you see, if you chip off some of the concrete from the top of this particular pile, what will happen, that reinforcement will get exposed of, which is here in this particular case. You see here, these vertical bars are seen, they are in the process in this particular pile, and then in this particular pile it has not been chipped off. So, you can see that the concreting is done and the soil cover is also there, little bit of soil layer is there. Now, how do you chip off the pile? See, once the concreting is done, and we really go for M30 grade of concrete. So, and if the compaction has been done properly, it becomes really difficult to chip off the concrete from that particular pile. So, with the help of this drilling machine, they just chip off that particular concrete. You must be wondering that first we completed the pile at 30 meter, and now we are chipping off this particular material from the top. Why exactly it is being done? So, the answer to this particular question will be obvious in the subsequent slides. You see, it is not that only pile will be there. You have to provide a connection in all the piles such that the load from the superstructure will come to these and will get distributed uniformly to all the piles and then to subsequent soil strata. So, this reinforcement of the pile will go in the in that particular structure which will be coming just on top of the pile. Let us say it is a kind of a raft that will come or that will join all the piles. So, we will be seeing typical view of that particular thing also, then you will be appreciating this particular thing, that why exactly it is necessary to expose of some of the reinforcement part from top of the pile. So, you can have a look that many workers are doing their work, some are drilling. Here you see that drilling part is going on, some are just washing off that particular area. On that day it was a rainy day. So, you can see some of the water is getting accumulated at different places. So, if you see at if you have a look on this particular thing, particular pile, what happens is you can see here that a typical lateral tie is also exposed in this case, and then these vertical bars, they have got bended like this in the different direction. So, likewise if you have a area and in that one you particularly design that how you have to provide these piles, what should be the spacing, what should be the arrangement, whether they should be arranged in triangular fashion or rectangular fashion or some other pattern, that you have to first decide upon and then only go for the construction. But this is how the situation looks like at any construction site, and this is how it looks above the ground. Then this is another view. You see here that all the piles they have chipped off the concrete from the top and they have cleaned it, and this is how I mean all the piles, you have the large area, many number of piles are there, some are being cleaned and some are there in the process of that chipping off and then cleaning of the concrete. As I was telling you that you see this is what is the this vertical bars, they which are visible here in this particular picture, they are the main reinforcement of the pile, and this is the grid which you are seeing. This one you can see that this is the particular grid that is for the raft. When you will be studying the shallow foundation, then you will you must have studied this kind of foundation, that isolated footing and then combined footing, and one particular type of shallow foundation is raft foundation. So, when the raft foundation is provided with this pile foundation, the combination is called piled raft foundation. So, to have monolithic in construction, that monolithic word means that the pile and the raft, they will behave as one single unit. It is not that when the load will be coming, the raft will behave separately and the piles will be behaving separately. No, they will behave as one unit. So, to be in monolithic in construction, to have monolithic construction, this thing is being done, that the reinforcement of the pile is continued till the raft is placed. That means that the main reinforcement of the pile gets into the raft also, to have monolithic construction. Then now you see, first we saw that what are the various types of pile, and then we had some of the pictures that I took from one particular construction site where the pile construction was going on, that how it is being constructed. Now, once it has constructed, we have to see that what exactly is the magnitude of the load that a particular pile can take, or what exactly is the load which a group of piles can take. So, its construction procedure is over. Now, the estimation of its capacity will be there. So, what exactly do we mean by that? How we can calculate that load carrying capacity of the pile in compression, that we will be studying in this subsequent slides. That in general, this is a general thing, general requirements for satisfactory behavior of pile foundations are adequate safety against shear failure and permissible settlement. The load capacity of pile can be estimated by several methods which may be grouped into several categories. So, as in case of shallow foundation, when you were checking that ultimate bearing capacity as well as the settlement criteria, likewise in case of pile foundation also, you have to see to it that pile is not failing against shear as well as it is not undergoing excessive settlement. That means one is from the safety point of view, another one is from serviceability point of view, stability and serviceability. So, the settlement should be within permissible limit as and along with that the pile should be safe against shear failure. There are various methods from where this pile load carrying capacity in compression can be estimated. Usually they are grouped in 4 categories, and they are that you can find out the load capacity of pile in compression by static pile load formulae. There are various formulae for different types of soils. Then by conducting pile load test in the field, let us say you constructed a pile and there itself you test it and find it out that what exactly is the load that it is taking. Then pile driving formula, depending on what type of hammer that you are using, what type of motor that you are using, depending on its efficiency and all other things, you can estimate this load carrying capacity of the pile in compression using this pile driving formulae. And then there are some correlations which have been developed over many years using the penetration data. I hope that you have studied that standard penetration test while you studied soil exploration chapter, and from there once you get the data that can be correlated to the load carrying capacity of the pile in compression. So, these are the mainly 4 categories from where you can estimate the load carrying capacity of the pile. So, let us start with static pile load formulae, that how we can find out the capacity of the pile using these formulae. When a compressive load Q is applied at the top of the pile will tend to move vertically downward related to the surrounding soil. Obviously, when you apply the load to any kind of a structure, it will try to displace. So, in the case of pile also, let us say that you are applying a load Q from the top which is compressive in nature, the pile will have the tendency to move with respect to the surrounding soil. And then this will result in shear stress to develop between the soil and surface of the shaft. There will be relative movement in pile shaft and the soil strata which is surrounding that pile shaft, which will develop the shear stress. So, as a result, the applied load is distributed as friction load along a certain length of pile measured from the top. So, as soon as the shear stress is developed, your applied load, whatever is that is applied load, this Q which is compressive in nature, it will get distributed as the frictional load along the shaft length. But earlier it will be to some particular length. Now, what will happen that when the load at the top will go on increasing, the length of generation of this particular friction load will go on increasing along the pile shaft. So, you see here, as the load at the top is increased, the friction load distribution will extend more and more towards the tip of the pile, till at a certain load level the entire length of the pile is involved in generating the frictional resistance. You remember when we were discussing about that end bearing pile and skin friction resistance of the pile, there also we saw this exactly the same kind of mechanism. What happens is that from the top, when the load is being applied, it will be getting applied slowly. You can just imagine a process of construction which will be taking place. Let us say first the dead load of any, you cannot just create, let us say if you are going for say 7-story or 8-story building, you really cannot go for, you really cannot construct 8-story building at one go. You will be going in stages. Let us say first you completed first story, then second, then third, and then subsequently the load will be increasing. So, the load is not applied suddenly, it is a gradual one. So, as you go on increasing the load on the pile from the top, the length along which the friction load is developed, it will go on increasing, and this length will go on moving towards the tip of the pile. One situation will come when the whole of the length of pile or the pile shaft will be creating or causing that whole friction load. In that case, that particular resistance is called ultimate skin friction resistance of pile, and we represent that by Q subscript F, that is QF. Can see here, this is ultimate skin friction resistance of the pile, where the friction load is getting mobilized all along the length of the pile shaft. It is only when the load at the top of the pile exceeds QF that the load in excess of QF begins to be transferred to soil at the base of the pile. So, you see the load is gradually increasing, and from there a situation will come when this friction load will get mobilized along the total length of the pile shaft, and that particular stage we are calling as ultimate skin friction resistance QF. So, at that particular situation or condition, your Q which is applied from the top will become equal to QF. Let us say that this QF you attain after the completion of construction of the second story, but you have to go till 8-story building. So, what will happen, that when you will start the construction of beyond this second story or the construction of third story, this Q value will go on increasing. The moment it increases the value of QF, that is the ultimate skin friction resistance, this will get transferred to the base of the pile. This load is known as point load, and this will go on increasing till the soil at the base of pile fails by punching shear failure. It is not that to the infinite extent you can go on increasing the load and pile can take that particular load. It has its capacity. So, the frictional capacity you can estimate using that QF. Whatever is your QF, that will be the frictional resistance or the capacity of the pile. In case the Q exceeds the value of QF, in that particular case, this remaining load, that is Q minus QF load, will get transferred to the base of the pile, and you can go on increasing the value of the load Q till the soil at the base of the pile fails by punching shear failure. So, whatever is the resistance of the soil at the base of the pile, that much only extra load you can put as point load. The load in bearing at this stage is called as ultimate point load, which is represented by QPU. P is for point, U is ultimate, that is ultimate point load. So, you got familiar with two terms, that is ultimate skin friction resistance and now this ultimate point load. Then the maximum load which the pile can support through combined resistance of skin friction and point bearing is known as ultimate load capacity, which we represent usually by QU of the pile. So, whatever is the distribution or how it is getting transferred, whatever the load which is coming on the pile, that is compressive load from the superstructure, first it will get transferred to the pile shaft in the form of frictional resistance, and once that particular stage is over where Q becomes equal to QF at and if the Q goes on increasing beyond that, then that particular increase will get transferred to the point bearing, and the sum of these two, that is ultimate skin friction resistance and ultimate point load, gives you the maximum load which a pile can support through combined resistance of skin friction and point bearing, which is called as ultimate load capacity or QU. It is notated by QU. So, you see here this QU will become equal to QPU plus QF. First one is ultimate point load, second is ultimate skin friction. If this QPU is quite high, then as compared to this QF, the pile may be called a point bearing pile. That means the soil surrounding the pile shaft is such that it is not able to mobilize that much of the friction resistance as compared to the ultimate point load. So, mainly the pile resists the load through point bearing, that is this QPU is quite higher as compared to QF. In that case, the pile is called as point bearing pile. Now, there can be another situation that if this QF is quite high as compared to QPU, then this pile is called frictional pile, that the resistance through friction becomes so much that the load which is coming from the superstructures is not getting transferred to the tip of the pile or the base of the pile. In that case, the function of the pile or the load transfer mechanism usually is by this friction only. So, in that case the pile is called the frictional pile. The relative proportion of loads carried by point load and skin friction, they depend on the shear strength and elasticity of the soil. So, you see, depending on the type of the soil which is lying surrounding the pile shaft, let us say if it is able to mobilize good friction resistance along the pile shaft, obviously the frictional resistance will be more, and then the pile will be acting as friction pile. And in case the soil is not able to provide that much frictional resistance, or in case the soil is lying below the the pile is resting on the good soil strata or maybe rock, then in that case the soil surrounding the pile shaft will not be able to mobilize that much of the frictional resistance as compared to the end bearing resistance, and so it will be acting as a point bearing pile. And then the vertical movement of pile required to mobilize full skin friction resistance is much smaller than that required to mobilize full point bearing resistance. This is a very important aspect, which is that vertical movement of pile required to mobilize full friction resistance is much smaller than that required to mobilize full point bearing resistance. So, you can see, first as soon as the load is coming on the pile, first the friction is getting mobilized along the length. Obviously, when the load is coming, the pile is getting displaced, from that the shear stresses are getting developed, and so they are resulting into frictional resistance. So, by the time your Q will become equal to QF, that is at ultimate skin friction resistance, the deflection of the pile is not that much. So, to mobilize the full point bearing resistance of the pile, you need large vertical movement of the pile. In clays and for driven piles in sand, the vertical movement required to fully mobilize the base resistance is about 10 to 20% of the base diameter. So, we really have to keep a check that what exactly should be the vertical movement, such that the total skin friction is being mobilized along the length of the pile shaft, and then beyond that the point bearing is getting mobilized. So, in case of clays and for driven piles in sand, this to mobilize the base resistance fully, the vertical movement is of the order of 10 to 20% of the base diameter. So, let us say if you are the diameter at the base is 1 meter, then Around 0.1 meter to 0.2 meter is the vertical movement that will be required to fully mobilize the base resistance. This usually implies that when piles are designed to carry a working load equal to 1/3 or half of the ultimate load, the chances are that the shaft resistance is fully mobilized at this vertical at this working load. So, usually what happens is that piles are designed to carry a working load equal to 1/3 or half of the ultimate load. See, ultimate load is being calculated using this static pile load formulae or any other measure, then it is halved or 1/3, and then the structural design of the pile is carried out using this particular halved or 1/3 of this ultimate load. So, as you can see that the base to fully mobilize the base resistance, you require 10 to 20% vertical movement of the base diameter. So, at this particular position, there are chances that the shaft resistance is fully mobilized at that particular working load. It may happen that the fully mobilization of point load may not take place. It has been observed that one case is that when the ultimate skin friction resistance is mobilized, only a fraction of ultimate point load is mobilized. So, first is that the skin friction is getting mobilized. So, whenever a load is coming from the superstructure to a pile, first it is getting mobilized along the pile shaft to a particular length. As you go on increasing this value of q, the length over which this will get mobilized, or the length along which the frictional load will get mobilized will go on increasing, and a stage will come where you will achieve ultimate skin friction resistance. So, when the ultimate skin friction resistance is mobilized, what does this mean is that at this particular point the applied load becomes equal to the ultimate skin friction resistance. In this particular case, only a fraction of the ultimate point load is mobilized. That is very obvious, and when you will increase the load which is coming from the superstructure beyond this particular stage, then this ultimate point load will go on increasing. And then the second one is, when the ultimate point load is mobilized, the skin friction resistance has decreased to a lower value than its peak. See, what is happening in this procedure is that as you are increasing the value of q which is coming from the superstructure, a condition is occurring that a particular condition is occurring that this load q is becoming equal to ultimate skin friction resistance. There will be a point when this point bearing resistance will be just equal to 0. When you will go on increasing the load, what will happen? The resistance which has been developed at the tip of the pile will go on transferring to the point bearing resistance, and in that process at any particular point of time, what will happen is that the ultimate skin friction resistance value will be always less than its peak value. So, that is what is there is the second point which we need to keep in mind, that when the ultimate point load is mobilized, the skin friction resistance will be reduced to the lower value from its peak value. So, today we saw that what are the various advantages and disadvantages of concrete piles, that is two types of concrete piles that we discussed. One was driven cast in situ and another was bored cast in situ piles. Then I shared some of my experiences with you as far as the construction of the pile is concerned. We saw that how that driving rig drives the pile, how high is that particular rig, then how this reinforcement cage is being lowered, what are the various techniques that is being adopted at as far as the construction of the pile is concerned, how the piles can be constructed monolithically to the superstructure or other parts of the foundation. And then after the construction, it was the point of concern that how we can find out or estimate the load capacity of the pile under the compressive loads. So, we saw that there are 4 categories that we can find out, or 4 ways that we can find out this load capacity of the pile in compression. They were static load formulae, then pile load test, and then dynamic load formulae, and the fourth one was correlation with penetration data. Then we started the detail of static pile load formulae, and in that one we saw that what exactly is the load transfer mechanism from the superstructure to the pile. We saw that when a compressive load from the superstructure comes to a pile, first the skin friction is mobilized. A condition is reached when this friction becomes equal to the applied load, and when this load is further applied, then it gets transferred as point bearing resistance. And then depending on whichever is the more, whether the ultimate skin friction resistance is more or the ultimate point bearing is more, the pile is named as skin friction pile or end bearing pile. We will see the mathematical details of static pile load formulae, how we can utilize them as far as estimating the pile load capacity in compression is concerned, and then we will proceed that how we can estimate the pile load capacity using in situ test and all other things in the subsequent classes. Thank you.